So let us talk about morphological image processing today. The important word is morphology. So it is a branch of biology. This is concerned with the form and structure of the plants and animals. So we will be seeing the form and the structure. And what about this mathematical morphology? This is a tool for extracting image components which is useful in the representation and description of image shape. And these shapes include the boundaries, the skeletons, and the convex hull. So we are going to look at morphological techniques for filtering, thinning, and pruning. So let us see the preview. The language of mathematical morphology is actually the set theory. We have learned this in basic classes. Set theory. So set is a mathematical morphology. It represents objects in an image. So objects, for example, the set of all black pixels in a binary image is a complete morphological description of the image, or a set of white pixel. This is also a complete morphological description. And for this binary images, sets are member of the 2D integer space z square, because binary image means z into z. Okay, in relations and functions we have seen that. So each element of the set is a tuple, means one from this 2D vector, whose coordinates are the xy coordinates of a black pixel in the image. Now grayscale digital images are represented in the set z cube. So z cube, what does this have? These are coordinates x, z into z into z. So we have coordinates x, coordinate y, and then we have this grayscale value. That is why z into z into z. And higher dimensional sets could represent attributes such as color, also time varying components, etc. Let us see basic components or concepts of set theory first. If A be the set in this z square z into z, and if this A is A1 and A2, this is a tuple, this is an element of A, then we write A belongs to A. This belongs to this set A. And if A does not belong to, we write this sign. This is the belonging, this is the non-belonging. A set with no element is called null or empty. If you have no element in a set, we say that it is a null or empty set, which is denoted by this sign phi. We call it phi. And the set is specified by the contents of two braces. These are the braces, and all elements are written here using comma. And for binary images, the elements of sets are the coordinates of pixels representing the objects. Right? The element of set for this binary image will be coordinates of the point for objects. So if we write an expression in the form C is equal to W, where W is equal to minus D, for all D this belongs to capital D, where we mean that this C is a set of elements. This W is formed by multiplying each of the two coordinates of all the elements of set D by minus 1. Right? This is an form of expression if you want to write. This W is what? This is formed by multiplying each of the two coordinates, means these two coordinates of all the elements of the set, every coordinate by minus 1. So if every element of set A is also an element of set B and vice versa, we say that A is a proper subset of B. The union of two sets will be A union B. This is written as A union B, means element of A and element of B or both. Intersection means A intersection B, means element of A and element of B which are common, the elements which are belonging to both A and B. And two sets are disjoint or mutually exclusive. Two sets are disjoint or mutually exclusive if they have no elements in common. Right? No element in common, that means there can be no intersection value. We say it is phi. And the complement of set A is set of elements not in A, that is A complement or A dash, where W is such that W does not belongs to A. And the difference of two set means the value of B, which is being eliminated from A. It is defined by A minus B. That means W belongs to A, but it does not belong to B, because the elements of B has been taken off from A. This is A intersection B complement. This is equal to A intersection B complement. Now local operations which involve binary images. This is A. Now principal logic operations are AND, OR and NOT. This is A, and if we talk about, or if we want to find out A naught, then all elements except this black portion will be not A. This is A and this is B, and if you combine them and only highlight that region which is common to them, we say A and B. We combine them and we take this and also the common area. So this is A or B. Then XOR means you combine them and you just delete that portion, the portion which is common to them. And this is not A and B means combine them and then reduce or eliminate this not, or difference you can take from this combine, or rather in a simple word, combine them and just eliminate A because it is not A. Now this is functionally complete means combined to form any other logic operation. These are principal logic operations, and logic operations described have a one-to-one correspondence with a set of operations like intersection, union and complement. So logic operations are restricted to binary images, not the case for general set operations. This is the basic concept from set theory. The reflection means of any set B is defined by, this is the reflection sign, W is equal to W is such that W is equal to minus B for all B belongs to B. So if B is a set, then all values will be minus B, right? This is the reflection. Means from plus to minus. This is the reflection, and the translation of set B by a point Z. This is Z1, Z2 is nothing but we are adding some Z to the actual initial value. C is such that C is equal to B plus Z. So the value will be, the Z will be added to each value of B. So this is how, this is a set, this is its reflection C, it comes like this. All the positive values will become negative value and you join them again and it will be like this. And this translation means it was lying here, see, and it was being translated, means it was being grabbed and kept at a certain other location. Now structuring element means set reflection and translation are used extensively in morphological operations such as structuring elements. The structuring element. So structuring element is a small set or sub-image used to probe an area of interest for certain properties. Probe means finding. So these properties may be of arbitrary shape and size in practice, and this structuring elements is generally a regular geometric shape, that is square, rectangle or diamond. So generally padded to a rectangular array for image processing. In this row, these are the example of structuring elements, and these are second row are the structuring elements which are converted to rectangular arrays, because ultimately we have to do some image processing. We cannot do it on this like. We have to have some square or a regular shape. So the dot, this dot denotes the center of this structuring element. So this, if you take just one example, the values or zeros or any values of your choice which you think that image processing will help, these values are being added. These are being padded. So we make a proper square or rectangle out of it, then do the image processing. So two-dimensional or flat structuring elements consist of matrix 0 and 1s and typically much smaller than the image being processed. So center pixel of the structuring element called origin, it identifies the pixel of interest and the pixel is being processed. The center pixel is being processed. So the pixels in the structuring element containing 1, this defines the neighborhood of the structuring element. So all these are, if we take this particular shape for image processing, these are the values which define the boundaries. Let us see the operation with structuring element. An example: this particular image or this particular shape is a set. Each shaded square is the member of the set. This is a structure element, and this is a set of padded with background elements to form a rectangular array. Rectangle or square you make and provided with a background border. This is a border also. See, the last padded area is the border. This is a structuring element as a rectangular array. We have made array for this also. And this particular shape is structuring element. This is a set processed by the structuring element, this element, right? So this was applied here, and applying, as we applied those values which are, you can say you have done union or intersection. So according to that, the final result of applying these two or combining these two in certain fashion will give rise to this element. So there are certain Matlab functions also, strel. This creates a morphological structuring element. What you do is strel, you pass the shape and parameters. This create a structuring element or SE of the type specified by this shape. So this is the table. It is which lists all the supported shape. And depending upon this shape, this strel this command may take additional parameters. You need to see the syntax descriptions that follow for details about creating each type of structuring element. Then we have reflect function also. It reflects structuring element. You just have to write reflect. And this structuring element, it reflects a structuring element through its center. So the effect is the same as if you rotate the structuring element domain 180 degree around its center. So this structuring element is an array of structuring element objects. Then reflect SE, reflect each element of SE, and SE2 has the same size as SE. This will have the same size. It was being reflected. So these are the class support. SE and SE2 are strel objects. We have this translate, and what this does is it translates structuring element. So it translates this SE in n-dimensional space. This V is the n element vector containing the offset of the desired translation in each dimension. Now let us talk about this dilation. When A and B are two sets in this Z square, Z cross Z, the dilation of A and B is noted by this plus sign, round plus sign, which is given by A plus sign means Z is such that this B cap of Z, this is an intersection of A, is not equal to null. So this formulation is based on the reflection of B about its origin and shifting this reflection by Z. First reflection and then shifted by Z. So the dilation of A by B is the set of all displacement Z such that B and A overlap by at least one element. So it does not become phi. Therefore, another expression for the dilation of A by B can be written as Z is such that B, this is the reflection, intersection A is a proper subset of A, and this B is nothing but the structuring element. This is the dilation example, right? Now this is set A, D by D. This B is actually the square structuring element. This dot denotes the origin, and this is C, dilation of A by B. This is shown shaded, right? And this is D, which is the elongated structuring element. and this E is the dilation of this A using this element, elongated element. So the dotted border is actually the C, and C is nothing but the boundary of set A. This is shown only for the reference. This is reference, but actual final result is this. And when we apply this, the final result is this whole. So B is equal to B, which is reflection, because B is symmetric with respect to the origin. It's just a reflection. This dashed line shows the original set A, and the solid boundary actually shows the limit beyond which and further displacement of the origin of this translated or reflected B by Z would cause the intersection of this set by A to be empty. So all points inside this boundary constitute to the dilation of A by B. The second case shows more dilation vertically than horizontally, right? So dilation application, one simple application of dilation is for bridging gaps. In the image below, the maximum break length is of 2 pixels. See, although low pass filtering can be used to accomplish the same task, this generates a grayscale image that must then be thresholded to produce a resulted binary image. So we have this A, as this is a sample text of poor resolution with broken characters. See this magnified view. This is the broken. These are the broken characters, and these are the structuring element. And this is the dilation. So this is the structuring element. And this is the dilation of A by B, and the broken segments were joined. This is the use of dilation. This is the dilation example of Matlab. So we have this IM dilate. You can use this IM dilate to dilate, and this is the structuring element. This is also an example of dilation. See, these all broken images are being covered or joined. Now we come to erosion. This A and B sets, if they are set in Z square, the erosion of this A by B, this is denoted by A. This is the sign of erosion, which is defined by Z, such that this BZ belongs to or is a proper subset of A. So in other words, erosion of A and by B is the set of all elements of Z such that B, which is translated by Z, is contained in A. So dilation and erosion are duals of each other with respect to the set of complementation and reflection. So A, this erosion B complement is equal to A complement, dilation of B, that is reflected, reflected image. And the same goes for this, same, just change the sign. So this is the erosion example. This is set A, this is the structuring element, and this is the erosion of A by B, which is shown as eroded. And along this D is the elongated structuring element, and this is the erosion of A by B using the same element. So the dotted border in C and E, this C and E is the boundary of set A, nothing but the boundary of set A, which was actual set, shown only for the reference. So erosion and dilation application, one simple application of erosion is for eliminating irrelevant details from binary image. In general, dilation does not restore fully the eroded objects.